Hello students, welcome back to the Tantra physics classes. Today I will discuss one more challenging problem with you on the forces between the conductors. As you may be knowing that if there are two current carrying conductors, they exert force on each other. And the problem is like this. You see, I have two conductors here. This conductor carries current I, let me suppose. Is a finite conductor, of course. This is not infinitely long conductor, and to this conductor is connected here a spring, here also a spring on both sides, and there's one more conductor here. I connect these two conductors, their ends by a spring, this also by a spring. And what happens if the current flows like this? The current gets back in a circuit, and the current flows through this coil. I mean, this conducting coil type spring. It is a spring which can carry current along with it, and this current flows through this coil, and the current flows like this and goes back like this. So it's a kind of a circuit, right? So the distance between the two conductors is L, and this distance is capital L. Length of each conductor is capital L. The question is, when the current flows like this, these two current carrying conductors, they will repel away each other. They will repel away each other. And when these two conductors repel away each other, these two springs will get stretched. I mean, they will try to extend. The moment they will try to extend like this, suppose they extend by this amount, this also extends by this amount, that's given to be D. The extension is given by D, and this spring creates force in the upward direction. There's F spring, and the force between these two is repulsive. That is, okay, F magnetic. The two conductors will create a repulsive force on each other, and they will repel away each other, and this spring will stretch, and this will extend. This will also extend by distance D, and because of this there will be a restoring force, the upward force, due to this force that will try to bring the spring back to this original shape, that is Fs. This is Fm, repulsive force. Magnetic force is repulsive, and they will this force will try to get the two conductors away, but when the two conductors get away from each other, the spring stretches, and that stretching of the spring will create a backward force. At equilibrium, obviously these two forces have to be equal. Otherwise, if the equilibrium is not achieved, then this will go on stretching. The springs will go on stretching. But equilibrium has to reach. A time will come when the Fs force, spring force, will balance the repulsive magnetic force. What we have to find? We have to find under these, given these parameters, length of the wire is L, and this relaxed length of the spring is L, stretch is D under this force. What is the spring constant? What is the expression for spring constant? K, we have to find this K, spring constant, in the form of expression. Of course, that spring constant should contain all these given parameters. That is all. That's the problem. Two current carrying conductors, the current is opposite from here, it is in this direction, from here in the opposite direction, they will repel away each other. They are connected through two springs, and the two springs, they are connected, the force, repulsive force, will stretch the springs apart, and that will create a restoring force. The force will try to bring the spring back to the relaxed condition. At equilibrium, these two forces have to be equal. At equilibrium, these two forces are equal, but at equilibrium, it has already stretched by d. It has also stretched by d, and we have to find the spring constant. That is all. Okay. Now, how to do that? Very simple. So, in order to solve this problem, I must explain you a few concepts before we solve this problem. The concept is like this. If these are two current carrying conductors, number one concept. Infinitely long. This carries current I1, this carries current I2. These are two current carrying conductors, and the distance between them, okay, let me suppose it is R. The two current carrying conductors parallel, carrying current in the same direction upwards, infinity long. They will create force on each other, attractive force. Why? Because this conductor is in the field of this conductor. This conductor creates magnetic field, and the second conductor is under the influence of magnetic field of the first conductor. So first conductor creates a magnetic field I cross R in inward direction. This is magnetic field inward. This magnetic field is due to this. And this magnetic field, I will write B1 because this B1 has been created by I1. Now the second conductor is in the domain of this magnetic field B1. So we already know if a current carrying conductor is in the magnetic field, it experiences forces. And that force is given by I cross B. I is this, B is inverse. I is this, B is inverse. I cross B, that is some towards this. So on this force we created, that is F21. This conductor is in the field of this current carrying conductor, and therefore there will be a force on this conductor. How much is the force? That is F21, but the direction of the force is this. Obviously that force F21 is equal to L, length of the conductor, I2 cross B1. That is the force on this conductor. Similarly, this current carrying conductor is under the influence of this magnetic field, but this will create magnetic field on this in the outward direction, B1, and again is I cross B. So current is this, and magnetic field due to this is this on this conductor, this. So I cross B, that is towards this, F12. So F12 is the force on this conductor, and F21 is the force on this conductor. And this is also very simple. F12 is again length of this conductor, I1 cross, but B2, because magnetic field created by this conductor on this conductor, that is B2, that is B2. And this is the concept. So the concept is like this. If there are two current carrying conductors carrying current in the same direction, they will attract each other. They will attract each other. That attraction is magnetic force, and that force is equal to F is equal to how much? When I solve this, it's easy to solve. I can find the magnetic field from here and substitute it here. I2 and B1 are already perpendicular, so it's I2 B1 sine 90. That is, it can be done very simply. So I will write the final expression, that's mu 0 I1 I2 by 2 pi this R and length of the conductor. This is the force on either conductor. Yes, if the currents are in the opposite direction, they will repel away each other. Very obvious. Two current carrying conductors carrying current in the same direction, they will attract each other. If the current is one upward or the downward, the two conductors will repel away each other. That's all. So that's one point that I try to explain here. Second point that I want to explain is that is a spring. What is the properties of a spring? Second point. Spring. Suppose this is a spring of natural length, whatever, L, and here's a mass connected to this. And I will pull this mass towards the right side. Let me see what happens. So this becomes like this. How much I have stretched? How much I have stretched this spring? Suppose X. The spring has a property to get back to its relaxed condition, to get back to its normal length. So it will create a force on this mass in this direction, F, Kx. With a negative sign, of course, when stretch is on the right, force is on the left. If this compression is on the left side, means if the spring is compressed like this, if spring is compressed like this, the force will be in this direction. That's why it is F minus Kx. Stretch is on the right, force is to the left. Stretch is on the left, compression is on the left, because the spring, when you get compressed, you have to push it to the left. The force is on the right. So that's why we write F squared minus Kx. So if X is more, if the stretch is more, or the compression is more, the force will be more. So this is a basic equation, spring equation, F is equal to minus Kx. Of course, the stretch should not be much larger. If it is much larger, then this equation will not be followed. This equation is followed only when X is moderate. X is not more than a certain distance. If you exceed that beyond, then this equation is not valid. Hooke's law should be followed for that kind of stretch or that kind of expression, compression. It should be followed. So F is equal to minus Kx is the equation, but this X is either stretch or compression. Right? So these two concepts I will apply here to solve this problem. Now see here. First of all, these two currents, this current is the same, of course, the same current flows like this. This current and this current, two conductors, they carry current in the opposite direction, therefore they will repel away each other. When they repel away each other, this spring will get stretched. It will get extended by D. When it gets extended by D, there will be a restoring force to get the spring back to its original shape. So what is Fm? Third, the solution. What is Fm? Fm, force between the two current carrying conductors, upper one and lower one, will be mu 0 I1 I2. That was I1 I2 there because there were two conductors separate, they were carrying different currents, but now it's the same current flowing through both the conductors. So it's I square by 2 times pi. What's the distance now between the two current carrying conductors? It is not L, because by the time there's a current flowing, it will repel away each other, and this conductor will go down by D because of the repulsion. So it is not L here. The way we write 2 pi r there, two conductors, we should write L plus D here into length of the conductor. We are following the earlier equation that we have given for two current carrying conductors, create a force on each other. So it is equation number first. Had this force been the only force, then it will go in a stretching way. It will continuously stretch. But this creates upward force at the same time, because the moment it stretches down, it creates an additional force. What is spring force? Yes, that is K spring constant that we have to find. It is Kd. Kd, force on this spring upwards and force on this spring upwards. Force on this spring upwards. What's that? Plus Kd again. So it is 2 times Kd. This spring will create upward force, this spring will also create upward force. Both the force added together is Fs. Right? So at equilibrium, what should I write? At equilibrium, Fm is equal to Fs. When these two conductors have stopped moving and the spring is already stretched, that is an equilibrium situation, like this. Equilibrium situation. There is, they don't move any further from here. So it is an equilibrium situation. We equate the two forces. At equilibrium, we should know the net force is 0. So what should I write for this? It is mu 0 I square by 2 pi L plus D. L is equal to 2 Kd. From here, can I find K? Yes. K can be determined. So what is K? That is mu 0 I square L divided by 4 pi L plus D, because this 2 will come down, it will become 4 here, and this D will also come down and it will be D here. This is the answer for the spring constant. That was the problem. Current carrying conductors connected through two springs, the current flows. Of course, we can't make the current flow like this unless we have a battery here. Battery should be in series with this, so current will flow like this, and then it will come back in a series circuit. And finally, we could find this D. We could find this K, spring constant, in terms of known quantities. I should be known, L is already known, D is known, and length of the conductor is already known. This was the one of the problems that I wanted to solve on the online. And here again, I ask you to download the app, the physics classes, which you can download from Google Store, and also follow me on the YouTube, so that you can continuously get my lectures on the YouTube. And from 5th, that's from tomorrow, I'll be starting rotational dynamics with the students. You have to follow the lectures very closely, and these will be taking some 18 lectures, and every lecture will be followed by a problem set. And this rotational dynamics will be completed within, I think, within 20 lectures. Thank you.